Hello and welcome to this video. In this video I'm going to be continuing looking at this tutorial exercise of analysing a rubber bellows component. In the previous video I showed how we built a finite element model of this component using the Axisymmetric technique on the 3DEXPERIENCE platform. Since then, I've started using a slightly different method of connecting SolidWorks to the 3DEXPERIENCE platform. So just to show how that works, I've got the same finite element model here, and I'm going to use this 3DEXPERIENCE task pane here. When I open that and extend it across the screen, you can see I've got this component here, which is tutorial 6, which is connected to the 3DEXPERIENCE platform. I've made some changes to this, so it's shown as not up to date. If I right click on this, I can click on save, and that component is then uploaded to the 3DEXPERIENCE platform and is then available when we go to the platform as a native piece of geometry that is linked back to this SolidWorks component. So any changes I make in the SolidWorks component, all I then have to do is resave in this task pane over here, and that will then be reflected in the geometry that's on the 3DEXPERIENCE platform. In the 3DEXPERIENCE platform, we have this model, which is functionally identical to the one that I created in the previous video, even though the source of the geometry has changed slightly. What I should have shown in the previous video, because it's part of the model rather than the scenario, is creating the tie constraints that join the platens to the bellows. So I'll just demonstrate that now. I've created the bottom one already. We'll run through how to create the one at the top. So the first thing I'm going to do is just hide a few bits of geometry just to make it easier to select what I need to select. So I'm going to hide the finite element model, and then under the abstraction shapes, I'll just hide the platens themselves to make selecting a little bit easier. From the connections area of the toolbar, I'm going to choose tie to make a tie constraint. The main surface is the rigid platen, so I'll select the upper one from the tree and then select this edge here on the bellows for the secondary surface. And I don't want to use the shell thickness as part of this, so I'll uncheck that option and click OK, and you can see the green and magenta dots appear to indicate that I've created that tie constraint successfully. I'll just show everything again just to configure the display how I want, and it's good to update regularly when you're building, but that's the tie constraints complete, and that's now the finite element model complete for this analysis. With the finite element model complete, I've now created a scenario using the mechanical scenario creation app and given both the analysis and the scenario meaningful names, which is a good thing to do. The first thing I'm going to do is select a procedure which defines the analysis step type, and for this I'm going to use a static step and choose an initial time increment of 0.05 seconds and a maximum time increment of 0.05 seconds, which I know from previous experience works well with this analysis. I'll OK that, and the step is created in the scenario area of the tree. The next thing I'm going to do is set up contact interactions, and so these are chosen from the interactions section of the toolbar, and I'm going to use general contact as a very straightforward way of defining these interactions. So I choose general contact, and all of the defaults in this dialog box are appropriate for the analysis we're doing here. So we have a general contact domain, which includes all surfaces and also self-contact. So I just OK that. The next thing I'm going to do is to set up the boundary conditions, which define the restraints and loading for this analysis. So I come over to the boundary conditions toolbar, and firstly I'm going to define a clamp on the top platen, and I'll use pre-selection filtering to help with this. So I choose Fem feature, and now I can pick from the rigid bodies. The top rigid body is the one I want to select for this boundary condition. So that's going to clamp that top platen in all of its degrees of freedom. For the lower boundary condition, I'm going to use two boundary conditions, one to apply some fixes, so fixed displacements. Again, I'll use the filtering for this and select rigid body 1 in this case, and I want to constrain that platen in all of its degrees of freedom apart from the axial direction, which is the Z direction. So I'll OK that. That's created another boundary condition. And then the final boundary condition is going to be an applied translation to move the bottom platen. such that it compresses the bellows. So again, we'll use the same method to select the support for this. I want to apply a boundary condition of 4 millimeters to displace. And as soon as I put that in, you can see an arrow has appeared here to show us how that's going to move. That's okay. All of the other defaults are as we want. So I OK that, and the boundary conditions are complete. That completes the analysis definition, but before I run, I just want to change the default element type assignment. So I double click that in the tree. The reason for doing that is that this model is using a rubber-like material with a hyperelastic definition, and hybrid elements are better suited to that type of analysis. So I'm just going to change the element types to these that have an H suffix on them, which defines them as hybrids, which should improve and help convergence. So I'll just change those and click OK in there. And the analysis is now ready to run, so I can go over to the Simulate tab, choose Simulate, and once the dialog comes up, I can configure my analysis. So I'm going to run interactively here on 4 cores, and this is going to use my embedded license. Once I click OK, the analysis should run. Because the analysis is axisymmetric, it completes very quickly, and once you close the simulation window, the result is displayed. I've looked a bit at post-processing in some of the other videos, so I'm not going to talk about too much here, but because this is axisymmetric, one option that is available is in the Display tab. You can sweep the geometry around its axis and configure that. And that gives a full 3D representative view derived from the axisymmetric results, which is a little bit more appealing. So sometimes when we finish the first analysis, it doesn't quite achieve what we wanted to achieve for the design. We need to go back to SolidWorks and make some design changes. Maybe add an extra convolution in there to change the properties. So we'll change that from 2 to 3, modify the design. When we want to analyze this, all we need to do is right-click here and save, and that's going to upload the new configuration into the 3DEXPERIENCE platform. If we go back into the 3DEXPERIENCE platform now, I've made the geometry visible just to make things a little bit easier to see what's going on. I'm going to go down to the Global Refresh option and click Global Refresh. And that gives a warning that we're going to update 2 objects, which is fine. So when I click yes, that happens, and we can see that the geometry has changed now to reflect the new configuration with the additional convolution in there. I now just need to update in order to make the finite element model representative of the new geometry. And now everything is updated. If I hide that again, we can see that the finite element model is as it should be. Update again, and we can see that the boundary conditions have now moved to the new position, and the new design is ready to simulate without any additional work being involved. Thanks for watching. I hope you found that useful.